walked away from that at least understanding what the atom is. So if I drew a proton in the nucleus, and I have an electron, and it's just orbiting like a planet, and then maybe I give the electron a little bit more energy, and it gets into a little bit higher orbit. So there's an electron, and then maybe it can jump up, maybe it can fall back down. Is that the quantum mechanical model? Oh. Why? There's quanta here. There is a discrete change in the orbits. Is that not quanta? We saw one of those models yesterday. So I heard several people say, no, that's the correct answer. This is not the most modern version of the. This would be representative of what was called the Bohr atom. Okay, so there's some quantum mechanics there, but it's not the correct model. This is the model that is being taught across the planet, okay, certainly across the United States, to grade school, middle school, and high school students, which is very unfortunate because it is absolutely wrong. It's not the right model. So can someone help me modify this? Let's keep the proton in the center of the atom. Let me erase the orbits. Okay, how would I model the electron? And a hydrogen atom has one electron. So let's do hydrogen. So how would I draw that on the board? This is what I wanted you to really know yesterday, by the way.
Isn't it a big cloud?
Ah! Dude, you're crushing it, man. I kept fist pumping you yesterday. All right. So here. So the electron, most people think of the electron as a little subatomic particle. We even call it a subatomic particle. It's actually mislabeled. It's a subatomic wave. And it's only when we do something to observe it. And it's not observing it with our eyes, it's observing it with scientific equipment or electronic stuff, that it collapses the wave into a particle. Okay, that's what's happening. So the electron, one electron, is a smear, it's a cloud, it's a wave. And so I could represent it as kind of a wave that is waving, and it's everywhere about the proton. There's the one proton, so the electron is that wave, and it is everywhere in that region all at the same time. So it's not a particle in that sense, it's a wave. And it's not until we hit it with a photon, hit it with light, or we try to measure it, that it'll collapse into a little point. And that little point can make little spots on electronic equipment. Okay, we have electronic components that can actually detect that little spot. They're called scintillators. I have one in my electron microscope that's in the lab that built that stuff, by the way, that's on the display. Okay, because we have to be able to see these tiny little things. But that is the modern version of the, and as the energy state changes for atoms, this wave smear pattern changes. You saw that yesterday in those clouds. It could have weird lobes. It could look like a clover. It could have it just depends on, so it's really bizarre. So if it's smeared into a higher energy state, say you have a wave, so you have a cloud here, and you have a cloud here, and a cloud here, and a cloud here, that wave is continuity between all those discrete regions. It's weird. It's super bizarre. And so there would be wave in here, a wave in here, and a wave in here. That's one electron. It looks like you're counting 4 different spaces. It's not. That's all just one electron for the hydrogen atom. And it's in between those regions where the probability is very low that the electron would be observed. So that's the true model of the atom. Are we all good with that? All right, I'm going to put a check mark. We accomplished something today. Okay, so these electrons, let's talk about superconductors. So so what happens in a superconductor, when we talk about conductor, we're talking about what's called electrical conduction. That is electrons moving from point A to point B in a material. Now that material could be like a copper wire in your house. So behind the wall are copper wires. and they can transfer electrons. But a conductive metal, okay? But also, that's an example of there's metal, the bright areas that you see in that diagram on the monitor from the cameras, that's actual live image. That is that bright area, the bright areas are aluminum, that's a metal. That's conductive, so that's a conductor. Okay, and then the darker areas, that's actually a semiconductor, that is silicon. So it semi-conducts. It's like not quite a conductor and not quite an insulator. So what is a conductor? That would be the question.
That's electricity pass through.
Yeah, I like that one. That's a good one. So electricity can flow, so to speak, through a conductor relatively easy. Okay, but let's modify it to sound a little bit more technical. The charge in a metal is electrons. So the electrons can move through the metal, okay, fairly easily in a conductor. In an insulator, so examples of conductors would be copper, aluminum, most metals, not all metals, but most metals are conductors. Okay, so you have insulators on the other side. So examples of insulators would be glass, okay, plastics, rubber, things like that. Those tend to be good insulators. So how would you define, in terms of conductance, the ability of electron to move from point A to point B? How would you define an insulator?
Creates a wall. So then electrons can't pass through.
Yeah, I mean there is a barrier kind of, the wall kind of thing doesn't necessarily flop. That's pretty good. And yeah, a complete one would be it impedes. An insulator impedes. It resists the flow of electrons. It doesn't readily allow. And so glass is a really good example. Glass is a good insulator. There's glass, by the way, on that chip. You just can't see it. Okay, but there's glass there. That's an important part of the materials that we have. So we have semiconductors, we have insulators, and we have metals and conductors, all on a silicon chip, all in your cell phone, making your cell phone work, all those little chips. We need all those materials. Okay, so then you have something in between. So kind of in between insulator and semiconductor, you have so insulator and conductor, you have a semiconductor. So it semi-conducts, but the important thing that I just want to mention just briefly is that we have a knob, okay, so we can do stuff to the semiconductor to make it more like a metal or more like an insulator. So I have control over that as an engineer. I can control that in the lab. It's super powerful. So I can make a semiconductor look more conductive by doing stuff in the lab or like in a fabrication facility in industry, okay? Or I can make it look more insulative. And then also electrically, I can apply like voltages like from a battery across a semiconductor, and I can dynamically change the conductivity of a semiconductor from more insulative to more conductive. That's actually the reason why semiconductors are so important in our world. It gives us all the stuff that you all love, all the electronics. I mean, that's the foundation of it. So let's talk about a metal. So if I think Mrs. Redmond, do you cover circuits?
Not with these guys so much. My physical science class did, but
Okay.
I don't think you guys have a lot of circuit knowledge beyond middle school circuits. Did you guys do circuits with Duffy? Yeah. No, maybe, kind of.
I don't
With a light bulb? No
So-
one remembers Duffy.
So this is a symbol for a battery. So if you just grabbed a battery out of a flashlight, this is just the symbol for a battery, okay, in electronics. And so this would have like your battery voltage on your little tiny like double A or triple A batteries. It's 1.2 volts on that battery. Okay, so if I have a normal wire, like a copper wire, and I connect it to a light bulb. So I have a little light bulb, it is sending out light, okay? then I could connect this battery to this light source and it will turn on the light, okay? And it's a flashlight. That's the simplest model for a flashlight. But what we usually do is we say, hey, the copper wiring has finite resistance. So when the electrons are going from one point to another point, what's happening is they're moving through the copper wire, but they're bumping into stuff. And what they're bumping into is copper atoms. They're bumping into copper atoms. That's called scattering. Okay, so it impedes, okay, or it resists that current flow. So it's actually labeled nicely. So the electrons that are moving from point A to point B in this copper wire are bumping into copper atoms, and it's resisting that flow. So that copper wire has resistance. It's actually called resistance. So so we model resistance in electronics by a symbol that looks like a little kind of sawtooth, and we label it with R for resistor. So I'm going to put this little resistor here to represent the resistance in the wire. So this is resistance of wire, okay? And so we can't help that. There's that copper wire, whether we like it or not, no matter what we do to copper, it's going to have resistance. Copper is not a superconductor. It has a finite resistance. It's resisting the electrons that are coming out of this battery. The battery are producing these electrons to flow, okay? So if I take a superconductor wire, okay, so now let's replace the wire with superconductor wire. That means this resistance goes to 0 ohms. Oh, by the way, I didn't mention this, but the resistance units has a omega, capital omega symbol, and it's called ohms. You probably have heard like maybe ohms before, maybe you can see that on specifications for stuff, you know, electronic stuff. Okay, so if I make this whole wire 0 resistance, and say I get rid of this light bulb, don't have a light bulb there, and I have 0 resistance, this is going to be what's called a superconductor, okay? And I switch, I get a current to flow, so I'm going to get electrons. So I'll just use E with a negative sign because electrons have negative charge, so I'll just E, that's my shorthand for electrons. So electrons are going in this loop. Oh yeah, that's actually the correct direction, so I got the direction correctly. So electrons are going out of the negative terminal of the battery. So they're going around this loop, and all of a sudden, if I could magically just switch out this voltage source and replace it with a superconductor wire. So there is just a loop of superconductor wire. Those electrons will go around that loop, as far as we know, forever. It has 0 resistance. The electrons don't bump into the atoms anymore. It looks like magic, okay? But quantum mechanics explains this. It is absolutely stunning. If we could do this, so there is a few problems. Not all materials are superconductors. There's a very limited set of materials that are superconductors. And as of right now, the world record highest temperature superconductor, don't quote me on this one, but I think it's like the coldest temperature in Antarctica is right about there. So we really want what's called room temperature semiconductors that you don't have to make super cold. So if you're in the coldest part of Antarctica, I guess you do have room temperature semiconductors at one form. But we would like superconductors to work at this temperature that we're sitting in this building. If we can do that, wow, the world is going to change.
Couldn't you just put the power stations in Antarctica?
Yeah, if they were just transferring power in Antarctica by itself, we'd be good.
We'll just charge big batteries, it'll be fine.
Kind of. Yeah, we've got some work to do, but yeah, for sure. So, okay, so the current will sit there, those electrons will go around this loop indefinitely, and they'll just keep moving. So that's the classical analogy to this would be if I took a track, a circular track with a ball bearing that could go around that track, and you flick that ball bearing and it started moving around that track, eventually it just like stopped. What is stopping it? Friction. Friction. It's like hitting air molecules, it's rubbing against the track, and it's going to stop. If that is a superconductor version of that, I'd flick that little ball, it would go around the track and it'd keep going around the track without any more push, without any more force, forever, as far as we know, forever. That's amazing. That is magical. Okay, so think about this for the utility of this, and I don't want to take up too much more time with this because I'm super passionate about this. We have to get electricity to this building for you to have lights in your computers and everything else. The power plant is potentially tens at best, or hundreds, or even thousands of miles away from this building. So when the power plant generates that power, it sends it down non-superconductor wire lines. It's sending them down wire lines, and you're losing electricity. There's resistance in those lines, and the amount of energy that's in those electrons that are coming to this building get lost. So we're losing. So we're generating all this power, whether it's like nuclear, fossil fuels, photovoltaics, thermal, whatever it is, we're still losing that power, and it's dumping that excess energy into the atmosphere, into the environment.
So like, if you stand under a carrier line, you can like feel it, you can hear it coming down.
Yeah.
Off of the line.
Yeah, totally. Yeah, totally. There's electric fields there. Sometimes you can feel static kind of on you for sure. Not a good place to be, by the way, in an electrical storm. So just FYI. But
cheap real estate though.
yes. So think about if we could have room temperature superconductor lines. We generate power in Florida, in Miami, and we send the power to Colorado. That's a long ways away. There's zero loss. You get all the power that was generated in Miami, it'll be present in this building with no loss. That's incredible. All right? That's a really huge benefit. And there's other equally exciting ones that are a little bit more technical for like computation, computers and stuff, but I'll leave it at that. So superconducting works like this. You take in a superconductor, you chill the system down, very cold, and you have two electrons that pair up. They start to pair up and they become like a cohort. It's called a Cooper pair. So Cooper was a physicist, and with two other scientists back in maybe early 60s, they got a Nobel Prize for this theory. It's called the BCS theory. Okay? And these little electrons pair up, and the two electrons can flow through the superconductor easier than one electron. That seems counterintuitive. That's weird.
What's the difference between a Cooper pair and an entanglement?
Yeah, so they're not really entangled. They're actually okay. So so one of my pastimes, lifelong, is I'm a surfer. I grew up on the ocean. I surf. So there's a good surfing analogy. So you're on the ocean. So we're going to use a surfing analogy. We're going to use surfers, and I'm going to represent the surfers as little dots. So what happens is you have an electron on the ocean, and it's an electron, it's a surfer, it's going to go this way. So what this first electron does is it's like pushing the water, and it starts to kind of push the water up, so it starts to make a wave. The water is analogous to the atoms in the superconductor material. Okay, so it's kind of pushing this wave up. And so as it's generating this wave, there's a whole bunch of electrons in a material. So an electron that's near this one, okay, it'll start to, this second electron so the electrons are moving in this direction. And this electron started making this little wave, so you have this wave, and this electron caused this wave, and there's another electron that starts to ride the wave with it. So this electron is surfing this wave, but this one kind of like snuck in behind it, and I'm going to surf the same wave. But this is kind of a loose analogy, okay? So You know, so, but the water in this case is actually what we call the lattice atoms in the solid. It's the actual atoms inside the solid. And they can actually move just a little bit because of the charge of the electron. So the electron is negatively charged, but the lattice atoms, when you take an electron off, they're positively charged. So it's pulling on it. So the electron is pulling on the water or pulling on the lattice, forming this wave. And this other electron, now negative charge want to repel, but the wave is enough to kind of hold those two fragilely together. And this only happens when the temperature's low, really low. This can happen. Okay, that's my best analogy without spending about an hour lecture.
They flow better in these pairs when the temperature is low.
Yes.
Great.
And when it's high, they don't have the wave to rise and they separate.
You